I just wanted to say that I just recorded the whole lesson and then realized that my microphone wasn't plugged in, so I have to do this all over again. Live and learn. All right, moving on. Section 5.2. Now, I said that I was going to have you keep on pausing, but you might want to pause, just copy down those objectives, and then we'll move on from there. So take a second to pause, copy down these objectives. Good? All right, moving on. What we're going to look at now in section 5.2 is another way in which we could collect data, and that's through using an experiment. We understand that a study is an experiment when we're actually doing something to the people or the animals or the objects in order to observe their response. We have some vocabulary that's specific to experiment design that we need to have under our belts. So let's run through some of this. First, we're going to say that the individuals on which the experiment is done, those are called the experimental units. The experimental units. When those units are human beings, they are called subjects. Also, when we have a specific condition that's applied to the units, we call that specific condition a treatment. The difference between an explanatory and response variable in an experiment is important. We call the explanatory variable in an experiment the factors of the experiment. They're often called factors. Sometimes you might have one factor, sometimes you might have different factors. More than one factor, you might have two or three. And these factors can be applied in different levels. So what you might want to do right now is grab your book, open up to section 5.2, pause this while you do it, and then I'll look at a specific example. All right, the example I want to look at is example 5.9 on page 290. Now, I'm not going to read through the whole thing here. Notice as you read it through yourself that they do go through and identify some of the vocabulary for this particular example. For example, they talk about how the subjects are these male physicians, that there are two factors, two explanatory variables, aspirin and beta-carotene, and we have two levels of each of those factors. Either the two levels of aspirin were yes or no if they took it or not, and the same thing with the beta-carotene. Once we know what our factors and levels are, we can determine how many treatments we have and what those treatments are going to be. And the easiest way to show this, sometimes if you have multiple factors like this example, is by setting it up in a table. For example, we know that we have one factor, that's my aspirin, and my second factor is the beta-carotene. Now, what they wanted to do is they took each of these factors at each level and made different combinations of them. For example, some physicians took the aspirin and the beta-carotene. Some of these physicians did take the aspirin, but did not take the beta-carotene. Some of them took the beta-carotene, but did not take the aspirin, and some of them took neither. neither the aspirin nor the beta-carotene. So you can see that we have 4 treatments with these different combinations of our factors, of the aspirin and the beta-carotene. Now, what they talk about on the next page is this idea that what we want to avoid is having these physicians know whether or not they're actually taking whatever treatment it is. So what they do is they use what's called a placebo. A placebo is a dummy treatment, a treatment that doesn't actually do anything. So these physicians didn't know whether or not they actually took the aspirin or not. They took maybe the placebo for the aspirin, might have been a sugar pill, for example, and they had some type of placebo for the beta-carotene. The reason for this is that there is documented evidence of what's called the placebo effect in psychology, this idea that people who think they might be receiving a treatment that's actually helping them, it might actually help them whether or not it's supposed to or not. So to avoid this placebo effect, we give them this dummy treatment. Now, a couple more vocabulary terms. The next one we're going to look at is what's called a control group. A control group is the group that is not receiving any treatment. For example, in this problem here, the group that did not receive the aspirin or the beta-carotene, they got the placebos for both. This is my control group. There was no treatment, so to speak, on these individuals. The control group helps us eliminate lurking variables. It allows us to compare the results that we get from the other treatments to there being no treatment. And that kind of leads us into our discussion of what the 3 principles of good experiment design are. Well, apparently, I thought I hit the record button, but I didn't, so I said a bunch of stuff that you didn't hear, and I think I remembered where I left off, but let's try this again. Hopefully I was talking about the principles of experiment design. There are 3 important principles. The first one is the principle of comparison. We understand from what we just said about the physician's experiment in that we want to be able to determine whether or not the aspirin and the beta-carotene are actually having an effect. The way I can do that is by having this comparison among our treatments, especially including the control group. That way we can tell whether or not one is different, the response of one treatment is different than the response of another treatment. A second principle is that of randomization. We remember from section 5.1 that personal choice leads to bias. We don't want to use personal choice to help us assign the subjects into those different groups for treatments. We want to use randomization, and we'll talk about how we're going to do that in a moment. And then finally, the third principle is what's called replication. Replication is using many subjects because we want to avoid chance variation in our results. If we just chose one physician for each of those 4 treatments, those 4 physicians there might be something different about them. There might be some lurking variable that might also be influencing whether or not they might get heart attack or not. So what we do is we take lots of physicians, place them into each of those 4 groups randomly, so that the idea is our groups are as alike as possible other than the treatment received. So replication and the randomization allow us to get as homogeneous groups as possible so that the only thing that's different about them is the treatment that's being received. Let's take a look at an example of how we can put this all together. Let's take a look at example 5.12 in your textbook. Are you there yet? Good. Example 5.12. So what they talk about in example 5.12 is describing how to design your experiment and what I'm going to be looking for. So we understand that we need randomization. So after you've read through this example, which maybe you're doing now as you listen to me, we understand that we always want to start off with a random assignment. We're going to take all of our subjects or all of our experimental units, and we want to randomly assign them into groups. We recognize from this problem that we have a total of 30 rats. We know that we're going to end up having 2 treatments. So we're going to randomly assign our rats into 2 groups. Group 1 will have 15 rats, and group 2 will have 15 rats. Then we'll assign a treatment to each group. We'll say that treatment 1 is the new diet, and we'll say that treatment 2 is the standard diet. And then in the end, our comparison that we're making is we're comparing the weight gain among all these rats to determine whether or not this new diet is helpful or if it's no different than the standard diet. Now, what you can see from this design is that we have all 3 principles of good experiment design. You can see that we have randomization. You can see that we have replication. We have more than one rat. We have multiple rats in each of these groups. So the idea is that each of these 2 groups is as alike as possible. Then what we do is we impose our 2 treatments, so we have comparison between 2 different treatments, and we have our response variable at the end. We're comparing the weight gain. And what we're going to look at is we want to know, is there a significant difference in these 2 treatments? If there was no difference between these 2 treatments, we would see that the 2 diets, the 2 weight gains, would end up being about the same. But if one is so much larger than the other, what we're going to say is that our results are statistically significant. We say that an observed effect so large that it would rarely occur by chance is called statistically significant. How large does it need to be? Well, we're not going to talk about that just yet. That's a whole bunch of chapters later on in the course. We'll get to it in about a month so we can judge whether or not one diet is more effective than the other. So the last thing I want to talk about is how we can assign our subjects to the treatments. So take a moment, flip back to example 5.12, and what you'll notice is at the bottom, underneath the diagram, they talk about how to do this assignment randomly. We understand that we have 30 rats, so what we're going to do is we're going to number them 0, 1 through 30. We might enter a random digit table, and they say use, for example, line 130. And we look for the first 15 rats that are chosen, and they make a list of them there, 0, 5, 16, 17, and so on and so forth. Once we have those 15 rats, those are the ones that are going to go into group 1, and then we'll say that the other 15 rats are going to go into group 2. So that covers this particular lesson. Do the best you can on those problems, and that'll do it for this particular lesson. Okay, thank you.